In this lecture, I'd like to close some loose ends so we can start solving two-dimensional stress-strain problems using two-dimensional triangular-shaped elements. The big payoff in our last lecture was this equation, which has three integrals in it, two volume integrals and one surface integral. It also has a point force vector. And this equation will actually end up yielding 6 equations and 6 unknowns. Remember, this term on the left-hand side is going to end up being our K stiffness matrix times our displacement vector U, which is a 6x1 vector involving displacements in the x direction and the y direction of our various nodes in the triangular element. This integral, which is a volume integral, is actually represents body forces. This integral represents surface forces. And this vector represents point forces at the nodes. Remember, at the end of the last video, I pointed out that I can simplify this volume integral because the B matrix nor the D matrix actually involves any term that is dependent on the x, y, or z coordinate. So since I'm looking at a triangular element of constant thickness and with a given area, I can simply rewrite this integral as the thickness times the area times the terms inside the integral. Likewise, even though that this is a triple integral of body forces, there won't be any z dependence, or we wouldn't have been able to model our problem as a two-dimensional problem. So this integral can also be converted into an area integral times a thickness. I can't move any further in this integral without knowing whether or not any of those body forces are dependent on the location in the xy coordinate. I can go one step further here. I know that when all is said and done, the thickness times the area, the B transform dB, will be converted and solved for a single stiffness K matrix. This K matrix being a 6x6 matrix, which will be multiplied by our 6 or 1 displacement vector. I pointed out that while the formula for the K matrix is given in your textbook, I don't actually encourage you for using that formula to derive this K matrix. At this point in the course, it's better to write a MATLAB or an Excel spreadsheet subroutine that, given your coordinates in the x, y, your xy coordinates for the 3 nodes, to derive the alpha, beta, and gammas 1 through 3, derive your B matrix, derive your D matrix, which involves properties of your material, such as Young's modulus and Poisson ratio. Multiply these 3 matrices together, which both MATLAB and Excel can do for you easily, and derive your K stiffness matrix for you. In the remaining videos in this lecture, I'm going to one by one go over the remaining terms in this equation, starting with the body force integral, then the surface force integral, and then we'll talk about the point forces. And then finally, in the last video in this lecture, we'll discuss forming the global stiffness matrix out of your various local stiffness matrices.